Welcome, delegates. Welcome to TMC 2021 Online. This session, like many others, has been pre-recorded and is available on demand. Refrigerated trucks and trailers, an often controversial subject and not necessarily simple. For this session, we have a single speaker who will focus on different aspects relating to parking outcomes. Greg Brown is the Engineering Support Manager for MaxiTRANS Group and has been in the transport manufacturing industry for more than 30 years. Greg is a mechanical engineer and has been involved in the development of many new products for freighter and MaxiTRANS over the years. Many of these products were innovative and first in the industry. Greg had a leading role in the development of the rigid drawbar converter dolly with ATA Industry Technical Council. The dolly has demonstrated the advantages of a rigid drawbar design in handling, vehicle stability, and overall performance on multi-trailer combinations. Operators with many different applications trialled the dolly and unfailingly returned positive results. Many have now purchased similar units. With that introduction, I will now hand over to Greg.
Thank you, Bob. I'll just share my presentation with you. At 30 years in the transport industry makes me sound old. I'm not really that old. I probably am. Yes. Okay. Today I just pass on some of my experience from the refrigerated trailers. So I'd like to cover 4 topics today. So outside wall colours, what does it do? Does it make a difference? What is this elusive K factor that gets bandied around the industry? Wall thicknesses, what difference does it make to the cold chain and the work that the plant has got to do, the fridge plant? And a little bit on multi-temperature zones and the importance of circulation. So outside wall colours. Dark colour walls do significantly increase the wall temperature when exposed to the sun compared to white walls. Most insulated vans in the country are white, and that works very well. Some are sign written, coloured for whatever reason, marketing, whatever. We just need to be aware that the darker the colour, the hotter it gets when it's exposed to the sun. If it's not exposed to the sun, it doesn't pick up the radiation from the sun. And if it's in the shade, it really doesn't make a lot of difference. Just to show that, I've done some experiments in the past. And if you see this yellow line, that's the dark colour wall. I parked 2 vans back to back in the sun, so they saw the same sun, they were the same walls, same trailers basically. One was dark colour, one was white. The dark colour one is here. This is the time of day down here, and the vertical axis is the temperature. The yellow is the dark colour wall facing the sun. The blue is the white wall facing the sun. And you can see the difference in the temperature from about 30 odd degrees to nearly 60. So it's nearly double the temperature. And again, on another day, so this is just a different day, a similar sort of difference. So the wall was up over 60 degrees. The white wall was down in the 30s. The green line is the dark colour wall in the shade, so not facing the sun. And the red line is the white wall not facing the sun. So there's a few degrees difference in those 2 colours when they're not facing the sun, but a huge difference when they are facing the sun. And generally there's only one wall facing the sun at any one time. So that makes it more difficult for the insulation because we've almost doubled the skin temperature of the panel. So that's where the leak comes from, the difference between the temperature inside and outside. It leaks through the insulation. So a dark wall is making that leak much, much higher. In fact, on a typical 25mm foam wall, which is a thin foam wall, with a 23-degree temperature difference inside to outside, it's about 965 watts for the dark colour wall compared to a white colour wall. So that 965 watts is leaking through the one dark colour wall, which is the fridge plant has got to pull that energy out to maintain the temperature. And if the temperature goes up to 38 degrees, it's 1200 watts leak a temperature difference of 38. So again, the fridge plant's got to pull out another 1.2 kilowatts or 1200 watts of energy out of the unit to maintain the temperature. So it makes a significant difference. It's generally on the walls. The walls are the biggest component of the single component of the unit. The roof and the floor are smaller. The front and rears are smaller again. So it makes you think about what should the roof be. You know, and sometimes, well, often we don't think about what is on the roof. It's dirty. In older days with older trucks, it was covered in soot and things from the exhaust. Not so bad these days, but some thought should go into maintaining the top of the trailer, the white colour, keeping it clean, as it sees the sun most of the time. So that will make a significant difference. The elusive K-factor. The K-factor is the material's thermal conductivity. So it's the conductivity of that material. That's what this K-factor does. The lower the number, the better. So it's how much energy that material will conduct per unit square area, so per square metre. The unit of measurement of the K is watts per metre thickness of the material, degree Kelvin, and in this case you can call that degree C. So it's how many watts will go through a thickness of the material for each degree temperature difference from inside to outside. That's what K is. It's not a good method to compare units. Some operators ask for this K factor. What's the K factor of the unit? And as a manufacturer, we provide that. But if you're comparing one to the other, the K factor is not really the best method to compare it, I would argue. I've done a little sample here with an Excel model I have to calculate the K factor and how much the unit does leak. And remember, the leaks are through the walls, the front, the rears, the roof, the floor. You know, there's lots of leak paths from inside to outside. But I've just plugged into the model for a similar spec, so same walls, same roof, but just two different lengths and what the difference in the K is. So I've got a 10 metre van and a 14 metre van. The K for the 10 metre van is 0.57. The K for the 14 metre van is 0.53. Now remember, these are all the same panels, same walls, roof, whatever. So if you look at that in isolation or without much knowledge, you would think that the 14 metre van leaks less than the 10 metre van. And of course, that's not the case. The 14 metre van leaks about 2.5 kilowatts. And this is at a typical 30-degree temperature difference inside to outside. And the 10 metre van is a 2 kilowatt leak. So a significant difference. But when you look at the K, it's the other way around. So you've got to be very careful that you know what K is. So effective wall thicknesses on the insulation. Generally, the thicker the foam on the walls, the better the insulation, and that's fairly logical. The thicker it is, the better it is. The walls are only one component of the leak in the van. There's lots of leaks. It's like a big bucket with lots of holes in it. The walls are one of the bigger holes. The joins and the corners and edges are the leaks. The roof's not such a leak. It's not as big. And the front and rears are smaller components again. So the walls are the single biggest component. If you add the two walls together, they're the biggest single surface area of the unit facing the outside air. So it is important for the walls to be reasonably well insulated. But there's a practical limit to how much insulation you should have. For every unit thickness increase, so you double the thickness in the walls, you don't halve the leak into the van, because remember, you're plugging one hole in the bucket and it's got lots of holes, you know, the front wall, rear wall, roof. Just to show that, I've plotted a graph for a 40 mil foam wall, which is a thick wall in these days. A 40 mil foam wall with a 30-degree temperature difference on a typical 13.5 metre long van. You have typical 45 foot, some people call them. Typical 30-degree temperature difference, that's -10 inside, 20-degree outside, so fairly typical. The wall will leak 2.5 kilowatts, the walls, at 40 mil. Add 25 millimetres to the foam, you go to 65 millimetre foam, you've cut that down from 2.5 kilowatts down to 2 kilowatts. So it's a 400 odd watt saving in heat leak. But you go another 25 millimetres, go from 65 to 90, which is quite a thick wall. Today we don't use those. It reduces it only another 200 watts because it's only one of the holes in the bucket, if you think of that we're starting to plug. So the other leaks become significant. So the most practical, logical thickness foam would be in this range, 40, 65. Go past 65, the return is not particularly good on the space, because remember the thickness of the wall pinches load space. So multi-temperature zones and circulation. It's very common in the supermarket industry to have multi-temperature zones because they want to, in one delivery, have dry freight, chilled products and frozen products all in the one unit. So the zones are separated off with various devices to separate them. Generally, the other compartments are run by chilled by a remote mounted evaporator. The fridge plant on the front has got the best capacity or the most capacity. It would be logical to have the frozen compartment at the front against that big capacity fridge. That's not always the way it ends up. So often the frozen is not against the front. It's one of the other zones, which is difficult, and that's dictated by the customer. You can't do much about it. But the important part is the circulation. So if you think about the freight sitting on pallets in the trailer, if it's touching the walls and touching the front and rear bunding or whatever that is, there's no circulation around the product. The product leaks heat, or the heat leaks into the product via the walls, floor, roof. Okay, so if it's up against the wall, no circulation through it, the heat leaks through it. So it leaks from the outside through the wall into the product. You need to keep a little gap there to keep cold air coming from the fridge plant, wherever it is, to keep that barrier down, because the walls, floor will leak. Most things are on pallets, so it's not bad at the bottom because the air circulation is free to travel under the pallet. But don't box it in tight, as in you have a nice cold space above the freight, but effectively it can be leaking out through the side wall and defrosting that freight up against the side wall. So circulation is very important. And try and keep the zones in the logical sequence: frozen at the front, chilled next, and dry freight at the rear. That's sometimes dictated by outside influences. Another feature that's becoming more and more popular in this country and others, the inside width of the trailer is dictated by what you've got between the load lock, double loader rails, whatever's in the van. That's the load space. So the space between the load lock and double loader rails can be foam, and that's becoming more and more common these days. So you use that available space. So without reducing the inside width of the unit, we've got more foam insulation in the wall, so we've increased that a little bit. So it might have gone from 25 up to 40 mil, something like that, and that makes a significant difference if you remember the graphs earlier. Okay, so that's a feature that's coming, and it's something we're thinking about when you're looking at new products. Okay, that's about all I have. Thank you. Any questions, Bob?
Thanks, Greg. Very interesting and one of my favourite topics. To the delegates, please direct your comments and questions via the comment box. But before we close, Greg, I've got a few questions for you. The first of those questions, and you sort of touched on each of these subjects, you explained the effect of dark colours on walls of insulated unit. And what do you think of the effect of colour, or how clean the roof is?
Yeah, I said I touched on that, Bob, and trucks are much cleaner now they're running. But if you think back a little bit, you look at roofs, yeah, they were almost black from the exhaust, the soot and stuff out of the exhaust. And yeah, most people keep their units looking pretty spick and span on the outside, the part you see, the side walls and things, but no one pays much attention to the roof. So it's just something to think about, because it'll be proportional to the dark wall data that I showed. You know, if it's nearly black on the top and that sees the sun all the time, so that it'll increase the heat leak through the roof significantly if it's dirty, or particularly if it's a dark colour, tending towards black. So keeping it clean is important, I think.
Yeah, I guess it's the old story of out of sight, out of mind. But I think there'll be a number of operators who, after hearing this session, will be up on the ladder having a look at how clean the roof of their fridge vans are.
Yes, because it equates to the cold chain, maintaining the cold chain.
Yep, that's right.
And or fuel in the fridge plant.
Yeah. Greg, if K-factor is not a good method of evaluating and comparing insulated units, how should we be doing this? How can industry better manage this?
I think if we were, and I do a fair bit of work in this space, if we're looking at one trailer compared to another one, which walls do we have, which floor, how much insulation here, there, and whatever, it's really the leak, and the leak in watts or kilowatts. That's the energy that comes from the outside into the cold space. Generally, it's cold inside and warmer outside. It's that heat leak. Whatever that heat leak is, it's no different to your domestic fridge at home. Whatever leaks in through the walls, floor, and wherever, you've got to extract that heat out. How do you do that? The fridge plant has got to do that, and that's running on diesel. The harder it works, the more diesel it burns. Or if it can't do it, the temperature starts going up inside, and you lose that maintaining the cold chain of that product, which can have detrimental effect on the life of the product. So it's the most the better way is to just look at the actual heat leak of that unit, and then it's a direct comparison from one to the other. And then you can look at the fridge plant and say, can I extract that amount of energy, yes or no, on this particular day with that temperature difference? Some days it'll get 40-degree temperature difference. That's really difficult for a fridge plant to maintain the temperature.
Yeah, agreed. Within the constraints of external dimensions, what do you think is the optimum or most practical thickness of foam in the walls of an insulated van?
Yeah, as I touched on at the start, the more insulation, the better. But there's a practical point. We can't have 100 mil thick walls. We lose too much load space, or we've got to make the units too wide. So I think the reasonable heat leak, it's probably around 40 to 60 millimetres of foam in the walls. And as I said earlier, the walls are the biggest single component, the two walls put together. So it's the important part to think about. And but it's a compromise between the overall width of the trailer and the load space inside. And I think the practical point is 40 to 60 millimetres. Okay.
Now I've got one final question for you to make comment on, is that many suppliers think that refrigerated trailers and freezer vans are there to bring the temperature of their product down. And I've been involved in a few debates where the goods haven't quite met the requirements at delivery. But, really, these are for maintaining temperature, aren't they? They're not for bringing volumes of freight from, -5 down to -18. That's a huge task to place on a fridge plant. Would you like to make some comments on that?
Yes, that's correct, Bob. The capacity of a typical fridge plant running at minus something degrees, it might only have the ability to pull out, say, 10 to 15 kilowatts. Now, if the trailer's leaking 7 or 8 in through the walls, its actual capacity to pull the energy out of that freight is quite small. If you put 20 odd tonne of something in there with a fair bit of water content, the amount of energy to reduce that freight by a few degrees is massive. It's many, many kilowatts. It'll have to be in there for 3 days or a long time. So the fridge plant really hasn't got that spare capacity to pull the freight down, particularly to try and get down to low temperatures. So it's important that the freight goes in at the temperature that you're trying to maintain, and then the fridge plant's just got to maintain it. And even then, that's a tough call on a 40-degree day if you're trying to keep ice cream inside the thing.
Yeah, and even a bigger challenge if the ambient temperature is 40 or 40 plus.
That's right, yeah. The fridge plant performance drops off as the temperature goes up outside, and it also drops off as the temperature goes down inside. So you're fighting this losing battle. A 40-degree day on outside and you're trying to keep -18 inside. It's a very tough call. The actual capacity of the plant is quite low. and the leak in the van is quite high. So you're fighting this never-ending return.
Okay, well, I think we'll wrap up now. Thanks for your presentation, Greg. Very interesting and very important for operators who are transporting chilled and frozen goods. To our delegates, thanks for your participation, and get those comments in via the comment box. Thank you.
Thanks, Bob.